GameSci.com. GameSci.com.
Heidi ho, neighbors! Time for a lesson on Big O notation, where we can determine fast, medium, and slow algorithms or data structures. There is an official notation for comparing algorithms/data structures. It's called Big O notation, as in order of, or big order notation. It is a relative measure of an algorithm or data structure's performance as n increases. We as people, we like to put things into category. If you've rented a car, you know about this. At the rental car counter, they'll ask you, what size car do you want? Do you want a small subcompact car for the lowest cost? A slightly bigger compact? A bigger yet midsize? Or the full-size luxury car which costs the most? We divide things into categories, and when it comes to rental cars, it's based on the size of the car. The smaller the car, the cheaper the price. The bigger the car, the more expensive the price. Storm categories are also divided up. Watch the Weather Channel. When a big storm is coming in, a Category 1 storm is the least severe storm. The storm with well, it's still a serious storm, but it has the lower wind speeds. Then you go to Category 3, Category 4, Category 5 storms. Category 5 storms are the most severe with the hardest winds and the most rain. We divide storms into category from the least severe to the most severe. Big O has categories too. We divide algorithms or data structures into categories so we can measure their speed or performance. Order of 1 algorithms or data structures are very fast. They're the fastest algorithms and data structures. Order log n are fast. They're good, but they're not quite as fast as order of 1. Order of n category big O algorithms or data structures are the medium speed algorithms, and order n squared are the slowest algorithms. We're just dividing algorithms or data structures into their speed or performance categories. But let's be clear. Big O is not an absolute measure of time. It's a relative measure as n increases. We're comparing the same algorithm against itself as the data size gets bigger. Big O measures the delta, the difference, when n, the data size, increases. To show you an example, let's look at the current world records in the sprints. At 100 meters, it's 9.58 seconds. At 200 meters, it's 19.91 seconds. And at 400 meters, it's 43.03 seconds. As expected, the longer the distance, the longer it takes to run. And that's what Big O measures. How much longer will it take as the data size n increases? As data size n grows from 100 to 200 to 400 items, how much longer will the algorithm or data structure take to process the data? We're measuring the delta or the difference here, not the absolute value or the absolute time. For Big O, the absolute times, the 9.58 and the 19.91, are not the important information. What's important is the difference times, the 10.33 and the 23.12. The difference between 100 meters and 200 meters is 10.33 seconds. That's how much longer it takes to run the distance if I expand from 100 meters to 200 meters. The difference between 200 meters and 400 meters is 23.12 seconds. That's how much longer it takes when I expand the distance from 200 meters to 400 meters. As you can see, as the distance doubles in length, the times roughly double. And I can say roughly double because Big O is not an exact measurement. It says roughly it's going to take twice as long. As data size n increases or doubles, how much extra time do we expect the algorithm or data structure to take to complete the same task? That is Big O notation. big O measures the delta, the difference in performance or time as the data size n increases. The first big O formula we're going to look at is called order of n, or a linear algorithm, where the amount of time needed is matched to the size of the data. Linear search of an unordered array is an example of an order of n algorithm. Let's do a find on 26 for an unordered array. What we're going to have to do is look at 9 of 13 items in this array to find 26. On average, we'll have to look at n over 2 of the items. Remember linear search. It's going to start at the beginning here at position 0, and it's going to go to 1, 2, 3, 4, looking for the match for 26. 5, 6, 7, 8. When it finally hits 26, the algorithm is done and will stop. Well, think about it. What if I double the size of this array? Well, I'm doubling the number of items I'll have to look at. On average, I have to look at roughly half the items. Now, sometimes it'll be at the beginning, sometimes it'll be at the end, but on average, I'm going to have to go through half the items during a linear search. Double the data, I'm going to double the time. Very much like our sprint times. If I double the distance, I'm going to double the amount of time it takes to run it. If I double the number of items in the array, I'm going to double the time it takes to find that item. If it takes 0.2 seconds to search 5,000 items, on an order of n algorithm, it's going to take 0.4 seconds to search 10,000 items. Just like the sprint time doubles, the search time doubles with an order of n algorithm. There's no way around it. If you're going to look at n number of items, you double the number of items, it takes twice as long to look. So an order of n algorithm is called a linear algorithm, and it means the time it takes to process the data will match or double with the size of the data. What if my data was 10 times larger? Well, it's going to take 10 times as long, people. That's what an order in an algorithm says. Let's look at something very different. Big O formula order of 1, or constant algorithm. This says the same amount of time is needed no matter what the size. Insert into an unordered array is an example of an order of 1 algorithm. What does that mean? Well, look how I've changed the sprint times. 9.58 to go 100 meters. 9.58 to go 200 meters. 9.58 to go 400 meters. This time has not changed. It takes the same 9.58 to go 100 as 200 as 400. That is an order of 1 algorithm. An order of 1 algorithm takes constant time. Same amount of time for the larger distance. Now let's look at an insert of 26 into an unordered array. You have to look at one array slot, always one slot, to insert into an unordered array. As long as I keep track of where the last spot is. So the last occupied spot is 8. I go directly to slot 8 and I insert my 26. I don't have to examine this data to get to 8. As long as I keep track of where the end of the array is, I can instantly insert into it. It doesn't matter if I had twice as much data. No difference at all. It would take the same time to complete the insert. Whether I was going to slot 8 or slot 16 or slot 32 doesn't matter. All I need to do is go to the end of my data and insert something at the end of my unordered array. If it took 0.2 seconds to insert when the data item had 5,000 items, then it'll take the exact same 0.2 seconds to insert with 10,000 items or 100,000 items. It doesn't matter. If all you're doing is going to the end of the array and inserting into that one slot, it's an order of 1 algorithm. Think about it. Array sub 8 equals 26 takes the same amount of time as saying array sub 8,000 equals 26, which takes the same amount of time as saying array sub 800,000 equals 26. It doesn't matter. All you're going to do is go to the end of the array and insert a piece of data at the end of the array. The computer does a simple math calculation to figure out where the slot is and inserts the data at that location. Doesn't matter that the numbers are bigger, it takes the same amount of time. Now, in the real world, I couldn't think of an example of this. So I had to go to science fiction and the TV series and movies from Star Trek. In Star Trek, they have this thing called a transporter beam, where you stand on a pad and it beams you someplace else. Well, if it took 9.58 seconds to transport you 100 miles, and it took you 9.58 seconds to transport you 200 miles, and it took you the same 9.58 seconds to transport you 400 miles, that would be an order of one algorithm. Order of one algorithms are the fastest algorithms. We like order of one algorithms. Order of log n or logarithmic algorithms. Slightly more time is needed as n increases. It's going to take a little bit longer as n or the data size gets bigger, but not much longer. Binary search of an ordered array is an example of an order of log n algorithm. If you compare it to our sprint times, if it takes 9.58 seconds to go 100 meters, it'll take slightly longer to go 200 meters, let's say 9.61. And it'll take slightly longer to go 400 meters, let's say 9.69. You can see that the times are increasing because the distance is increasing, but it's increasing very slowly. That's what a logarithmic algorithm does. As my data set gets bigger, it takes longer to do it, but it only takes slightly longer. Let's do a binary search or a find of 85. You'll look at most 4 array slots. 2 to the 4th equals 16 to binary search this ordered array. Remember what binary search says. Start in the middle. Look at the middle item, 52. 52 is less than 85, so I need to search the other half of the array. Well, to search the other half of the array, I go to the middle of that half. And I go to slot 9 and say, look at the 79. Well, what I'm looking for, 85, is larger than 79, so I'll take the half that remains and search it. I'll go to the middle and find my 85 after just 3 comparisons. I didn't have to look at 10 or 11 or 12 items. I had to look at 3 items to find my data. It'll take slightly longer if my data size increases. If it took zero point 0.2 seconds to find the item within 5,000, then it's going to take 0.2001 seconds to find the item within 10,000. My data size increased. The time it took to find my data increased, but it only increases slightly. Now, understand why this is, you've got to understand power of 2 arithmetic. If I double the size of my array, that just means I have to look at one more item. It'll take slightly longer, but not much longer. The rough way to estimate how many comparisons it's going to take to find something in an ordered array is powers of 2. Notice that 2 to the 10th equals 1024. That means I'm going to have to compare 10 numbers to binary search 1024 items. Now, why is that so? Well, this 10 basically tells you how many times you can split 1024 in half. Think about it. 2 to the 4th equals 16. I can split 16 and a half 4 times. If doubling to 10 times will get me to 1024, then chopping it in half 10 times will get me back to 1. Another way to look at it is 2 to the 10th equals 1024. Log base 2 of 1024 equals 10. What the logarithm does is it finds the power of 1024 that it takes to get to 1024. Log base 2 is the opposite of the power of 2. Now let's go back to our Star Trek transporter beam. A transporter beam would be order of log n if it takes slightly more time to beam you 200 miles versus 100 miles. The transporter beam has to send your molecules some way. Even if it sends it at the speed of light, it takes longer for light to travel 2 different distances. And if it sends it at the speed of sound, it's definitely going to take a longer time. If it takes 9.58 seconds to transport you 100 miles, and it takes 9.61 seconds to transport you 200 miles, and it takes 9.69 seconds to transport you 400 miles, that would be an order of log n transporter beam. The fourth big O formula we'll look at is order of n squared, or an exponential algorithm or data structure. That means it's going to take much more time needed as n increases. Bubble sort of an unordered array is an example of an order of n squared algorithm. All the slower sort algorithms run at big O order of n squared. How would this work? Well, look at my sprint times. 100 meters, 9.58. 200 meters, 43.03. That's a huge increase in amount of time. 400 meters, 160 seconds, 0.91. Notice how it takes to go the distance dramatically increases as the distance increases. Well, sort algorithms perform this way. If you were to sort this data, you'd have to look at 13 slots to move 99 to the largest position. The way bubble sort works is it scans the entire data set, every piece of data, to move 99 to the end of the data. So it had to look at 13 items to move 99. Then it goes right back through the same data and looks at 12 of the slots to move 85 to that position. And so on. If I were to move the third largest number, I'd have to look at 11 slots to move the third largest number to here. You're constantly going through the same data over and over again to sort it. Well, if you increase the size of the data, the time it takes to do that dramatically goes up. If it would take 0.2 seconds to sort 5,000 items, it might take 0.8 seconds to sort 10,000 items. Think about it. 3 squared equals 9. 4 squared equals 16. 5 squared equals 25. As n increases, 3, 4, 5, n went up a little bit. N squared dramatically increases, 9, 25. There's only 2 difference between 3 and 5, but there's 16 difference between 9 and 25. An exponential algorithm goes up fast, and the bigger my data gets, the more time it takes to process that data. Going back to my non-computer example of running a distance or traveling a distance, let's talk about running while carrying a heavy weight. Let's say a sprinter with no weight on their back can do their 100 meters in 9.58 seconds. But then you take that same sprinter and say run it with a 50-pound backpack. Well, with a 50-pound backpack, it may take a lot longer. You can't run full speed with a weight on your back. You're going to move much slower, and it's not going to double the time it takes to go the distance. It might quadruple the time. Increase the weight. Now run 400 meters with 100 pounds on your back. Well, you're barely walking with that much weight on your back. It's going to take you much longer to go the distance. The longer the distance, the higher the weight, the slower the progress. That's what an order of n squared algorithm says. If I increase the size of my data, it's going to take much, much longer to process that data. If a sort algorithm is going to continually go through this data over and over and over again, you increase the size of the data, the time it takes to process it, it's going to go dramatically up. I'm going to wrap this up by confirming or reiterating Big O is a relative measure of an algorithm or data structure's performance as n increases. Thought about using the speed of light as an order of 1 algorithm and the speed of sound as an order of log n algorithm, but that would be wrong. Both the speed of light and the speed of sound are order of n, just like the sprinter is. Big O is a relative measure. Our perception of light is it's instantaneous. You light up one side of the room, it lights up the other side of the room at the same time. But a physicist will tell you light has a speed and it takes time for that light to move from one side of the room to the other. Even though it's instantaneous to us, an order of 1, light does have a speed. It takes twice as long to go 2 light years as it takes to go 1 light year at the speed of light. Sound is the same way. When you think about sound, there's a flash of lightning in the night sky, and you count the number of seconds until you hear the sonic boom. Sound travels fast, but it doesn't go as fast as the speed of light. It seems to me more like order of log n. But when you think about it, sound has a measured speed. It takes twice as long to go twice the distance. So both light and sound are big O order of n. did read an example on the internet. I can't remember exactly where, so it's hard for me to cite where I got this algorithm from. It was one of those Yahoo things. In my feed in Yahoo, it said, here's explaining computer science concept big O notation. And they had a great example. Can an order of one algorithm take 24 hours? And the answer was yes. Let's say you order a DVD from Amazon next day, shipping, and you'll get that DVD 24 hours later. Contrast this with downloading that same DVD. It's a large DVD, you're on a slow internet connection. Maybe it takes you 8 hours to download the same DVD. So you've got a choice. Next day air, I can get it 24 hours later, or I can start a download and get it 8 hours later. But what if you ordered 10 DVDs from Amazon? You want to go on a binge DVD watching spree? You can order 10 DVDs next day air from Amazon and you'll get 10 DVDs 24 hours later. The same amount of time it takes you to get one DVD from Amazon, you can get 10 DVDs from Amazon. But if you were to download those same 10 DVDs, it'll take you 80 hours to get them. You can't download two things at the same time. You have to download one and start the other. Amazon DVDs are order of one. It takes the same 24 hours when n increases from 1 to 10 DVDs. That is an order of one algorithm. It takes the same amount of time to receive one DVD as it takes to receive 10 DVDs, 24 hours. However, the download of the DVDs are order of n. If you take twice as many DVDs, it takes the twice amount of time of downloading. So that's my short introduction to Big O notation. I want you to start looking at algorithms and data structures from a speed or performance standpoint. There's algorithms we've already looked at and data structures we've already looked at. And I want you to kind of go through your mind and think, oh, well, what speed do they run? I've already told you binary search is the one that goes order of log n. What about the stack? Push and pop from the stack. Push and pop from the stack are order of one algorithms. All you have to do is look at the top of the stack and you're done. Doesn't matter whether the stack has 10 items or 10,000 items or 100,000 items on it. It's an order of one algorithm to push or pop from a stack. What about traversing a linked list? If you start at the beginning of the linked list and you start jumping from link to link in the linked list, guess what? That's an order of n algorithm. If my list is longer, it's going to take longer to traverse the linked list. If I go from 1,000 items in a linked list to 10,000 items in the linked list, it's going to take 10 times the amount of time to traverse that linked list. As we look back and as we look forward, start looking at algorithms and data structures from a speed or performance standpoint and put them in their Big O notation categories. That's what really separates a good programmer or a good computer scientist from a bad one. A good computer scientist knows before they write the code how well this software will perform. A bad computer scientist waits till after the code is written, then they realize, ooh, this is too slow, it'll never work in time. Thank you and talk to you later.